Okay, so we'll talk about the Perry-Robertson formula later on, which has replaced Rankine. But before we do that, let's just talk about tangent and reduced modulus theorems. So many materials do not quite follow what steel has followed in terms of the shape of the stress strain curve. So if you remember, carbon steel goes like that with the plateau, it goes like that, and then it suddenly fails. There are materials such as stainless steel, and stainless steel is different from carbon steel, and the most significant difference is the roundness of the stress strain curve. So a stainless steel stress strain curve would not have the E going up there to the plateau. It may go more like that. So there's a roundness to the stress strain curve, which is all great. I've obviously exaggerated that roundness, but you can see that there's a roundness there. So aluminium, stainless steel, not carbon steel, of course. They exhibit non-linear stress-strain relationships, but without a clearly defining yield point. So with carbon steel, you can say that's a yield point. With other materials, including stainless steel, you can't say that because they have a round stress strain curve. For such materials, there is no clearly defined constant Young's modulus, of course, because the stiffness keeps on changing. So with the carbon steel, we know we've got zero stiffness there, but with the stainless steel, the stiffness values just keep on reducing along the curve. So recall that Young's modulus is one of the parameters required to calculate Euler pi squared EI over L effective squared, and so the lack of it does pose a problem for using Euler's theory. However, for such materials, we can calculate what's known as the tangent modulus, which is the slope at the stress strain curve at a particular stress strain value. So we can say we wanted the tangent at that point there. What you could do is, when you do your coupon test, you could unload it, and if you unloaded it, it would, go back down here. So I think it's better if we explain it here. So anyway, the tangent stiffness is just obviously stress over strain, but taking the gradient of the round stress strain curve at whichever point as a substitute for the Young's modulus. Under certain assumptions, Essinger proposed for such materials replacing the standard Young's modulus with the tangential modulus for the calculation of buckling load and stresses. And so we've got ET there and we've got ET there. So this is the so-called tangent modulus theorem. Experimental tests, however, show that it does underestimate, or it can underestimate, the buckling loads, and observe that buckling initiation bending moment starts in addition to the axial load on the concave side of the cross-section, and it's compressed even stronger and deforms according to the tangent modulus. So as you load your specimen, you've got the convex side and the concave side, and you've got effectively different stiffnesses or different values of E on both sides. So the buckling expressions, since the E is not constant on both sides, or the stiffness is not constant on both sides of the section as it undergoes buckling, use the reduced or double modulus, and this is given by that equation there, so just the substitution of ER for ET. So the reduced modulus depends on the shape of the cross-section. So for a rectangular cross-section, that would be the equation for for ER. So measured buckling loads tend to lie between the lower line given by the tangential one and the upper bound given by the reduced one. And the simple Euler buckling load will of course be higher than them both, since the Euler buckling load would be using the gradient right at the bottom there, which of course is much stiffer than the gradient there. Since the reduced modulus load is on the unsafe side, it's more common to use the tangential modulus, which is also simpler to calculate. So determination of the buckling loads using tangent and reduced modulus theories requires an iterative solution. So when you're designing aluminium, or if you're designing an aluminium column, for example, and they are becoming more and more common in structural applications, or if you're designing a stainless steel column, which is already quite common, stainless steel is of course a lot more expensive than carbon steel, but the cost of it is coming down all the time. So I think at the moment it's about 2.5 times more expensive than carbon steel. But if you use stainless steel instead of carbon steel, your service life, or the lifetime of your structure, can be much longer, and you also don't need to worry about having to come back and paint it every 10 years or so for rusting. So stainless steel is becoming more and more common, as is aluminium, which is also very light. And when you use those design standards, you need to have an appreciation as to the changing roundness of the stress strain curve, and that's all you need to do when you follow the standards. Okay, so let's talk about Perry-Robertson. So the formulas used in New Zealand for steel structures. So this would be NZS 3404 for steel structures. So I myself use 4600 because I sit on the code committee for that, and I sit on that, and it's thin-walled steel. So my speciality is using very thin steel for building structures. But the heavy steel is 3404. So like the thin-walled steel, or the Eurocodes, or the American design standards, or the standards in almost every country, they would use the Perry-Robertson formula. I'm pretty sure that's Perry, P-E-R-R-Y, so I get that corrected. That expresses the condition for the onset of the yield stress in an axially loaded, initially curved column. So in section 3.2, we derive the expression for the total deflection of the column with the lack of straightness, and that returns us back to equation 29. So let's go back to 29, which tells us that the total deflection is equal to the initial imperfection plus the additional deflection. So we're back to equation 29. So at mid height, halfway up the column, we get that expression there, where A is the initial deflection at mid height. You're gonna start wondering what the initial deflection is. These days, as I said, we've got laser scanners. We can actually measure the initial deflection at mid height pretty accurately using the laser scanner, but that value is not to be substituted for A, because A also takes into account other things such as residual stresses, etc. So it's not just the fact that the column is not initially perfectly straight. We're just lumping all of these things into some equations that are quite easy to use. And after all, everything is tuned to the experimental data set that we get from our laboratories. So A is the initial deflection at mid height. Bending moment produced by load P. This equation would be given by that expression there. So that's just the moment multiplied by A. And the maximum compressive stress, we've done this calculation before, stress is equal to force divided by area, which is the axial component, plus the bending component, and then we re-express it in that form there. Y max is the distance from the neutral axis to the extreme compression fibers. So if we had a section like that, then of course we know the centroid is there, and if that's the tension side and that's the compression side, then Y max is the distance from there to this fiber here, since we know that the strain distribution would be something like that, so it would be maximum up at the top there. Where Y max is the distance from the neutral axis to the extreme compression fibers, and then we know that expression there, R is equal to square root of I over A, radius of gyration. So R squared is I over A, sigma equals P over A, and sigma PR is equal to P CR over A. And then re-express that equation, you get this form here. The column is assumed to reach its limit when sigma max up there reaches the yield stress, so we can substitute sigma max there as sigma y, and introducing our tuning coefficient, eta is equal to ay max over r squared, we can get this equation here. So just like with the Rankine, we had A as the tune to tune it. Here we've got eta. So it's the same story. We've got the same experimental data set, and you're just trying to pass a nice curve through that, and that nice curve comes from that which I presume is called the Perry-Robertson equation. So you can solve the lower solution, so that's just a quadratic which you can solve, which contains your tuning factor, of course. So you can solve it, and then you can get the capacity of the column exactly before. The capacity of the column is NC for the capacity, and that's equal to the stress from the Perry equation multiplied by A. So exactly the same process as the Rankine. So the coefficient eta depends on initial imperfections, and tests conducted by Robertson led to the assumption that eta is 0.03 L over R. So this equation then became known as the Perry-Robertson equation. So Robertson stuck his name onto the back of the Perry formula, which is quite common. Nowadays, the value of eta has been refined, and it slightly differs depending on the types of steel beams and the order of that. You actually don't need to know what the value is. So in design, instead of stresses, we often use load capacities. So it's the same, the load capacity divided by the squash load, or the load that causes the stresses, all to go into sigma y. And so we've got a load ratio or a reduction factor. So if your reduction factor is 1, then you've got a very short column and buckling is not important. And if your reduction factor is 0.1, NC over NY being your reduction factor, then you've lost 90% of the squash load capacity of that steel column to buckling. So then we get that equation, just re-expressed, we get that equation there. So the design standards, 4600 as well as 3404, they would provide this graph. So if you check the New Zealand standards, which effectively sits on the desks of all steel designers or all engineers, it would have these curves here with different tuning factors, and you just basically, all you have to do is work out your slenderness, read off whichever curve is appropriate. So a box section would have a different reduction curve to an I section, for example. So depending on the section type, you would be on a different curve, which the standards would clearly tell you. And all you've got to do is go up here for the slenderness and then read across. You've got the reduction factor and you've got the capacity of the column. So the curves are plotted for example values of that and that with a yield stress of 300. The particular value of slenderness of 44 is just used in a subsequent example but has no general significance. So again, very simple to use. Exactly the same as the Rankine. We've got the same column fixed and propped at the other end and made with steel. What is the axial load capacity according to the New Zealand design standards, which contains the Perry-Robertson equation? So all you do is read off 44. Using the Perry-Robertson equation, you can read off 44 from there for the slenderness, or you can plug it into the equation and get an answer to as many decimal places as you want. But using the Perry-Robertson equation and based on that one, which would be that curve there. So remember, whatever section you have, the standards will tell you which buckling curve to use. So that's not a decision that you have to make. We obtain a reduction factor NC over NY is equal to 0.9, which has been read off there. And since NY is the squash load, which is the cross-sectional area multiplied by 300, multiply those two together and you get 1053 kilonewtons. So flicking back with the Rankine equations, we were getting 925. So the Rankine gave you 925. Both are tuned to experimental data, but the Perry-Robertson is of course more more recent, and you can see that it's got a higher strength than the Rankine. So in practice, a strength reduction factor of 0.9 would be applied to obtain a reliable load capacity, and it's not greatly different from what you got from Rankine, just a bit higher, probably by about 5%, I would say, probably about 5% or so. So very simple equations, and that was used in the midterm test on 2017 and also 2016. So now we come to the tutorial, to the questions. So full solutions for all these questions are given in the Dropbox. You split them up into basic problems. So a basic problem is something that if you don't know how to solve, you will really run into problems in the exam. So make sure that you can solve all of the basic problems, and for each of these there's a code. You can look it up in the Dropbox and it will give you the solution. So those are what's termed as the basic problems. Then we have the advanced problems, which are more advanced than the basic problems. And again, for all of the advanced problems, the solutions are given in the Dropbox. So I would expect you to, maybe I would expect you just to read the solutions of the basic problems, but maybe you could do some, you could actually sit down and try and do some. So generally I tend to take exam questions, you know, mix them up and stuff. Generally I take them either from the in-class questions, as you can see here, or I might be mixing up a basic or advanced question problem. So these are the advanced problems. Again, full solutions provided. And then we come to what's known as the exploratory problems. So you can definitely get an A in this course without being able to solve an exploratory problem, but some of you might want something a bit more challenging, and that's where the exploratory problems would be coming in. And for these solutions given in the Dropbox. So I have used that one in the 2016 exam as an exploratory level question, but you'll probably see that there weren't too many marks associated with that question. Okay. So then we move on to the buckling problem sheet 2. So again, basic problems. Remember, you must know how to calculate the second moment of area of the section, so we can see the basic problems, and then some advanced problems, which you can see here, and then finally the exploratory level problems. But again, solutions have been provided for you to dip into, but don't worry too much if you can't handle the or you don't wish to handle the exploratory level questions. Okay, but please make sure that you can at least handle the advanced level questions for your examination. So this bit here is you can see the past test questions that have been said in the past. Obviously the students at that stage would have been given some very strong hints as to what the question might be. So you can see the Perry-Robertson equation and stuff like that. Midterm tests. This one here, that was a midterm or class test given before. And then these are the final exam questions, and you can see very, very similar to what you can see in the advanced levels questions. Sometimes I just take it, sometimes I mix them up sometimes I mix them up with other sometimes I try and combine two questions together or something, so you get something you've not seen before, but nothing you get should be a complete shock to you. For these, the TAs have provided video solutions, which they tell me will be put into the appropriate Dropbox folder for you to watch. But again, there's nothing particularly too complicated about it. If you've got any questions, let me know. But that is the end of the buckling lectures for this. So plenty of questions for you to dip in. And if you've got any problems, just post them up on Piazza. Send me an email or something, or just let me know what additional help or support you might need. Don't feel shy to ask. And if you need something, just let us know.